Week 10 contents. In this week and next week, we will use 2 weeks to study impulse and momentum. Impulse and momentum method may be adopted to easily solve many problems involving force, velocity, and time. Some of these problems can also be solved using kinetic equations of motion plus kinematics of rigid body. But for some of the problems, impulse and momentum method may be the only solution. I think impulse and momentum method is one of the most difficult topics in this subject. It should be helpful to have a brief review of impulse and momentum you have learned in particle dynamics. Firstly, linear impulse and momentum. It starts from the second law of Newton. The summation of all external forces on a particle is equal to its mass times its acceleration. Acceleration A is equal to dv dt. We can rearrange this equation by moving dt to the left side of this equation. Then we do integrate on both sides. In a process from time t1 to t2, the velocity of a particle changes from v1 to v2. Okay, now on the left side, this is the integral of f respect to time. Here, this f may be a variable or a constant. On the right side, this is the integral with respect to velocity v. We know mass m is a constant, so left side can be expressed using mv2 minus mv1. In this equation here, mv is linear momentum of a particle. The integral of f respect to time t is called linear impulse. It measures the effect of a force during the time the force acts. For example here, from t1 to t2. Both linear impulse and momentum are vectors. Z have magnitude and also direction. In this diagram, a particle has a velocity v. mv is its linear momentum. Now, how to calculate its angular momentum about a selected point? When we talk about angular momentum, we have to have a point. For example here, we select point O. Then we can calculate the angular momentum of this particle about point O. The magnitude of this angular momentum about point O is equal to its linear momentum mv times the distance from point O to mv. Angular momentum is also a vector. Its direction may be determined using right-hand rule. Principle of linear impulse and momentum of a particle. This principle tells us in a time period from t1 to t2, a particle's initial linear momentum mv1 plus a linear impulse on the particle is equal to the particle's final linear momentum mv2. As similar as this, principle of angular impulse and momentum of a particle tells us in a time period from t1 to t2, a particle's initial angular momentum plus the angular impulse on this particle is equal to the particle's final angular momentum. Angular impulse about a selected point, for example point O, is equal to the integral of the moments of all the forces acting on the particle about point O with respect to time t. Okay, now after this brief review of impulse and momentum in particle dynamics, next let's learn how to calculate linear and angular momentum of a rigid body. Then we will learn how to use the principle of impulse and momentum to solve a problem of rigid body involving force, velocity, and time. We already knew how to calculate the linear momentum of a particle. We can sum the linear momentum of all the particles of a rigid body. Then we can obtain the linear momentum of a rigid body. Please note, momentum is a vector, so the summation is the summation of vectors. Linear momentum of a rigid body L is equal to its mass m times the velocity of the mass center point g, Vg. Its direction is as same as the direction of Vg. The SI unit of linear momentum is kilometer per second. The calculation of angular momentum of a rigid body must be about a selected point. An arbitrary point P may be selected to calculate the angular momentum of a rigid body. Here are the expressions. The first one is in terms of the velocity of point P, and the second one here is in terms of the velocity of the body's mass center point G, Vg. If the selected point P coincides with mass center point G, then you will see in this diagram x bar and y bar, these two will become 0. Angular momentum of a rigid body about the mass center point G is equal to the MMI of the rigid body about an axis through point G times the angular velocity omega of the rigid body. The direction of this angular momentum is as same as the direction of omega. Here, please note, any points may be selected for calculating angular momentum of a rigid body, but different magnitudes will be obtained. This is very different from the calculation of kinetic energy of a rigid body. Any points may be selected to calculate kinetic energy of a rigid body, but only one magnitude may be obtained. We studied this in last week. A suggestion: work and energy method and impulse and momentum method are very different topics, but you may be confused by their directions, the principles, and the conservation theorems. So, I suggest it should be helpful to compare the knowledge of these two topics in your learning. A rigid body may undergo translation, rotation about a fixed axis, or general plane motion. For all these motions, the linear momentum are always the same. It's always equal to mvg. But for angular momentum, we can have some simplifications. So for example here, for translation, omega, angular velocity omega must be 0. So this means if we calculate the angular momentum about mass center point G, then Hg is equal to Ig times omega. Omega is 0, so Hg is always 0. We can select other point, for example point A, to do this calculation. If we select the point A, then the angular momentum is not necessary to be 0. It will be mvg times the distance from A to mvg d. In rotation about a fixed axis, for example here, this rigid body, its mass center point is G, is undergoing rotation about a fixed axis through point O. And here, the linear momentum, L, is still mvg. If we select the point G to calculate its angular momentum, it will be Ig omega. Sometimes it will be convenient to compute the angular momentum of this rigid body about the rotation center point O. Okay, in this case, we will have two items. One is Ig omega, and another item is mvg times the distance from G to O. We can rearrange this equation and apply parallel axis theory. So finally, we can get I0 omega. In this rotation about a fixed axis, if O coincides with G, that means if mass center point G is the rotation center, then Vg must be 0. So in this case, L will be 0. HO will be equal to Hg and equal to Ig omega. In general plane motion, linear momentum is still mvg. Angular momentum, if the calculation is about mass center point G, it will be Ig omega. But of course, we can select other point, for example point A, to do this calculation. We will have two items. One is Ig omega and another one is mvg times the distance from A to mvg. A special case is if this point A is the instantaneous center of zero velocity, then as similar as we did in rotation about a fixed axis, we can rearrange this equation and using parallel axis theory, and finally we'll get the angular momentum of a rigid body about its IC point should be equal to IC omega. We can use this example to show how to calculate angular momentum of a rigid body about a selected point. In this problem here, at a given instant, the angle between this slender bar and the ground is 30 degrees. And this bar has a mass of 5 kilo. This bar is falling down, and we know this is general plane motion. We already know the velocity at point A. How to determine the angular momentum of this slant bar about point G and about its instantaneous center of zero velocity at this instant. Okay, now let's solve this problem. We have defined this problem. We know this bar AB undergoes general plane motion. So we can draw a kinematics diagram. And in this diagram, at point A, we have VA, vertical downward. At point B, VB, the direction must be to left side, and this is horizontal. So using IC method, draw a line perpendicular to VB going through point B, another line perpendicular to VA going through point A. The intersection point will be the IC point. If IC point here, then we can easily determine the angular velocity omega of this bar AB at this instant, and also we can easily calculate the velocity of mass center point G, Vg. Vg must be perpendicular to a line connecting IC and point G. Okay, here we already know the mass of this bar, the length of this bar, VA. We don't know VB, omega. The target here is HG and HIC. HG, the equation is IG omega. HIC, for this calculation, we can use these two items, but we also can use IIC omega. Okay, so firstly, we can work out omega. And we know the distance from IC to point B, from B to point G. And then using trigonometry, we can work out the distance from point A to IC. Then omega must be equal to VA divided by the distance from A to IC. By observation, we know this omega must be clockwise. And here, I defined a coordinate system. In this coordinate system, X direction, right side, Y positive direction, upward, and clockwise is the positive rotation direction. Okay, now we can calculate Hg and HIC. Firstly, Hg. We need Ig because this is a slant bar, so we can use the established equation about point G. MMI of this bar is equal to 1 over 12 ml squared. Use Ig times omega, we can work out the magnitude of Hg. And this direction of Hg should be as same as the direction of omega, clockwise. HIC, we can use IIC times omega. How to calculate IIC? We can use parallel axis theory. So finally, we can work out HIC. Its direction is also as same as the direction of omega. Okay, here, if we compare the magnitude of Hg and the magnitude of HIC, we will see they are different. So this tells us we can select any points to calculate angular momentum of a rigid body. But the magnitudes won't be same. When we use impulse and momentum method to solve a problem, we need principle of impulse and momentum for a rigid body, or the theorem of conservation of momentum. So firstly, principle of impulse and momentum. Principle of impulse and momentum for a rigid body allows a direct solution to some problems involving force, velocity, and time. If the duration of time can be measured, the problem may also be solved using kinematics and the kinetic equation of motion. But using principle of impulse and momentum should be much easier. If duration of time cannot be measured, for example, in an impact problem, the impulse and momentum method may be the only solution. The procedure of obtaining principle of linear impulse and momentum is as similar as that in particle dynamics. Okay, so we still start from the second law of Newton. Ag is equal to dvg dt. G is the mass center point G. We can rearrange this equation by moving dt to the left side and then do integrate on both sides. On the left side, we have an integral of external force F on the rigid body with respect to time. On the right side, we have mvg2 minus mvg1. We use an impulse momentum diagram to help explain principle of linear impulse and momentum. In this diagram, firstly, we show the initial momentum of this rigid body. And here include linear momentum and angular momentum. In the middle, this one is impulse diagram. We show all the impulse generated by external forces and couple moments on this rigid body. Finally, we have a final momentum diagram. And here we show the linear momentum and angular momentum. Principle of linear impulse and momentum tells us the summation of all impulses created by the external forces acting on the rigid body during the time interval from T1 to T2 equal to the change in the linear momentum of this rigid body during the time interval. In other words, the initial linear momentum of this rigid body mvg1 plus all impulses on this rigid body must be equal to the final linear momentum of this rigid body mvg2. Using same procedure, we may obtain principle of angular impulse and momentum. We start from here. The summation of all moments about mass center point G of a rigid body is equal to Ig alpha. Alpha is equal to d omega dt, so we can rearrange this equation by moving dt to left side. Then do integrate on both sides. On the left side, we have an integral of mg with respect to time t. On the right side, we have Ig omega 2 minus Ig omega 1. The principle of angular impulse and momentum tells us the summation of the angular impulse acting on the rigid body during the time interval from T1 to T2 is equal to the change in the body's angular momentum during this time interval from Ig omega 1 to Ig omega 2. In other words, the initial angular momentum of this rigid body, Ig omega 1 plus the summation of the angular impulses on the body must be equal to the final angular momentum Ig omega 2. When we solve a problem in our calculation, we use scalar equations. In planar rigid body dynamics, if we define the motion is in the xy plane, we resolve linear impulse and momentum into x direction and y direction. The center of mass, point G, must be used here. The application of angular impulse and momentum can be about mass center point G, can be about any other point, if that point can provide us convenience. In some problems, we will have more than one rigid body. In a system consisting more than one rigid body, if we consider these rigid bodies all together, for linear impulse and momentum, the mass center point of each rigid body should be used. But for calculating the angular impulse and momentum, a same reference point O must be used for every rigid body. Now, a few examples that can be related to impulse and momentum. The first one here is impact of a tennis ball. And we know the mass of a tennis ball is not large. However, its impact may be very high if this tennis ball has a high velocity. The velocity may reach about 180 km per hour when served by a professional athlete. Let's watch a video. The motion of the balls in snooker and billiards is a typical problem of impact and may be solved using impulse and momentum method. The mass of a bird is very small comparing to that of an airplane, but its impact is high enough to damage the plane because the very high relative velocity between a bird and an airplane in the sky. No. Applications. Mass is always not uniformly distributed in a swing bridge. More mass is near the rotation axis. Why? Because this can reduce MMI of the swing bridge, so the torque or the time required to obtain a certain angular velocity can be reduced. Okay, so this is the equation of principle of angular impulse and momentum. mg is the torque. T1 to T2 is the time interval. If more mass is near the rotation axis, then this will be helpful for reducing MMI, for example, Ig here. Here, there is a video to show a swing bridge in Newcastle. And here, more mass is near this rotation axis. Some other swing bridges. This one, Tower Bridge. Its opening and two sections. You can easily find the rotation axis is here for this section, and more mass is near this rotation axis. This one is a swing bridge in Darling Harbour. Opening, more mass is near the rotation axis. We watched a video before to show the mechanism of a Chappie test. When designing this test, we must make sure the kinetic energy of the pendulum can be absorbed by the test specimen. But how can we make sure? We watched a video before to show the mechanism of a Chappie test. When designing this test, we must make sure all kinetic energy of the pendulum can be absorbed by the test specimen. But how? This can be solved using impulse and momentum method. There will be one example problem to explain this. Next, we will solve a couple of problems using principle of impulse and momentum. The first problem, and here you can see there is a wheel. The mass of this wheel is 300 kilo. Mass is not uniformly distributed in this wheel, but we know the radius of gyration about its mass set point O. KO is 0.4 meter. This wheel is subjected to a couple moments, 300 Newton meter. Now, this wheel starts from rest. This is the rolling without slip at the contact point between this wheel and the ground. The target is the angular velocity after 6 seconds. So this is a very typical problem we can solve using kinetic equation of motion plus kinematics of a rigid body. And here you can see this problem. This problem involves force. Force here is a couple moment of 300 Newton meter. It involves velocity. The target is angular velocity. And time. The time here is 6 seconds. So this problem, we can solve it using principle of impulse and momentum. Okay, the solution. We define this problem. We know this wheel is undergoing general plane motion. It's a rolling without slip. Next, we will have impulse momentum diagram. We establish a conventional coordinate system x, y, but here, just for convenience, we define clockwise is the positive rotation direction. Because in this one here, by observation, we know the angular velocity, its direction should be clockwise. Okay, initial momentum. Here we have linear momentum mvg1. 1 is initial position. we have initial angular momentum I0 omega 1. In the middle, this is the impulse diagram. We indicate the impulse generated by all external forces, including weight force W, reaction force N, friction force F. And here, this friction force is static friction force because no slipping at this point A, the contact point between the wheel and the ground. And also MT, the angular impulse. Here, final momentum diagram. And here we have final linear momentum MVG2 and final angular momentum IO omega 2. We already know the mass of this wheel, radius of gyration about point O, the couple moment, the time period from T1 to T2. T1, we define T1 is 0. So T2 will be 6 seconds. Initially, this wheel is at rest, so omega 1 should be 0. A target is omega 2. Okay, we use the principle of impulse and momentum. So firstly, principle of linear impulse and momentum. We can have two equations. One is along x direction, another one is along y direction. O is the mass center point. So here we express velocity using the velocity at this mass center point, VO. The third one is principle of angular impulse and momentum. And this can be about the mass center point O, but it can also about point A. For solving this problem, you will see using point A is most convenient. Why? Because A is the IC point. If you look at this impulse diagram, you can see about point A, the moment arms of weight force W, friction force F, and reaction force N, they are all 0. So to select point A for calculating angular impulse will be very easy. And here, because our target is the angular velocity, omega, so we will start from the principle of angular impulse and momentum. And actually, you will find, for solving this problem, principle of linear impulse and momentum, the first two equations are not useful. Okay, we calculate initial momentum and we calculate the impulse, angular impulse about point A. And here, final angular momentum. We need MMI of this wheel about point A. We already know I/O can be easily calculated using radius of gyration KO. Then we use parallel axis theory, so we can calculate IA. MA must be calculated. MA is the moment generated by all external forces about point A. As indicated just now, the moment arms of weight force W, friction force F, and the normal force N, they are all zero. So finally, we only have the couple moment M. So MA is equal to M. Omega 1 is zero. Substitute all these parameters into this equation, and we will find we only have one unknown parameter, omega 2. So this omega 2 can be easily calculated. It's positive, so this means omega 2 its direction should be clockwise according to the defined coordinate system. As mentioned, we can solve this problem using kinetic equations of motion. We can use kinetic equations of motion to find the angular acceleration alpha. Then, using kinematics, because we already know the time period. If we can work out angular acceleration, we already know the time period is 6 seconds. Then we can work out angular velocity in the final position, omega 2. But comparing this method using principle of impulse and momentum, you will see using principle of impulse and momentum should be much easier. This is a direct method. Next example problem is about a Chappie impact tester. For a Chappie impact tester, we know initially this pendulum is at a position where it is at rest. The velocity is zero. After releasing this pendulum, it will get a velocity. This means it will get kinetic energy. When this pendulum hits the test specimen here in the bottom, if we assume this pendulum stops after hitting this test specimen, then the kinetic energy must be absorbed by this test specimen. If we can make sure all kinetic energy of this pendulum is absorbed by this test specimen only, then we can use this energy to assess the mechanical property of this test specimen. Okay, this sounds easy, but actually it's not so easy. Why? Because when this pendulum hits the test specimen, impact may occur at the pin at this point A as well. So this means when this pendulum hits the test specimen, there is the impact here, and also there is impact at the pin at this point A. So this means this pin will absorb some of the kinetic energy of the pendulum. So when we design this Chappie test machine, we must make sure the impact at the pin at this point A is 0. In this problem, we already know the distance from the mass center point G of this pendulum to this A. The pinpoint is R bar. This is the distance. So what we need to do is to determine RP, the distance from this point P where the impact with the specimen from this point to A. If we can find a correct relationship between RP and R bar, then we should be able to make sure the impact at this point A, the pinpoint at this point A, is 0. Okay, now the solution. So firstly, we can define this problem. We know this pendulum rotates about a fixed axis through pinpoint A. When this pendulum hits the test specimen, if there is an impact occurs at this pinpoint A, this impact force must be along horizontal position. So this means, based on our analysis just now, we must make sure AX is 0. If AX is 0, then that means all kinetic energy of the pendulum can be absorbed by the test specimen only. And here is the diagram. In this diagram, at the pin point, we have AX, AY. At the mass center point G, we have weight force W. When this pendulum hits the test specimen, there is a reaction force from the test specimen to this pendulum. This is F. The acting point is point P. We use the XY coordinate system, and here we define clockwise is the positive rotation direction for our convenience, because in this one here you can see the angular velocity, its direction should be clockwise. We will use impulse and the momentum method to solve this problem. So we must have a time interval. For solving this problem, we can define the final position is immediately after impact, immediately after the pendulum hits the test specimen. But how about state 1? And here we define initial position is a position immediately before impact, immediately before the pendulum hits the test specimen. At this instant, the pendulum is already vertical. Vgx can be expressed using omega 1 times the distance from mass center point G to A. And Vgy at this instant must be 0. Why? Because at this instant, the pendulum is at a vertical position. So this means point G will be at its lowest position. So Vgy must be 0. To select this instant as the initial position can simplify our solution. Okay, and you can see initial position is immediately before the pendulum hits the specimen, and the final position is immediately after the pendulum hits the specimen. So the time interval between this initial position 1 and the final position 2 is very, very small, and this cannot be measured. So for this kind of problem, it's impossible to solve by adopting equations of motion and kinematics. And this kind of problem may be solved using impulse and momentum method only. Okay, now we have already know Rg, the distance from G to A. We already know Kg, the radius of gyration of this pendulum about point G. We know Ax must be 0, and we know omega 2 must be 0. If omega 2 must be 0, then you know Vgx must be 0 in the final position. Vgy, of course, is 0 because at this instant, immediately after the pendulum hits the specimen, test specimen, point G is at its lowest position, so of course it should be 0. We don't know Rp, the distance from P to A, and we don't know Vg1 and omega 1. Okay, now we will apply principle of linear impulse and momentum along x direction, along y direction. And we will apply principle of angular impulse and momentum. And for this problem, the calculation can be about the pinpoint, also the fixed axis through point A. Okay, along x direction in the diagram, you can see we have only f and ax here. Along x direction, f and ax, only these two. So here, we already know ax is 0, vgx is 0, so we can have this equation. We can express vgx using omega 1. The purpose here is to eliminate one unknown parameter, because vgx and omega 1, these two are not independent, they depend on each other. So we express vgx1 using omega 1. This negative sign shows the direction of vgx1. It should be to left side, so it should be negative. Okay, in this equation, f is unknown, omega 1 is unknown. Now, the second equation along y direction. Along this direction, we have ay and weight force w. vgy1 and vgy2, both of them are 0. So from this equation, the only thing we can get is ay should be equal to w. So this equation is not very useful. Now the third equation, principle of angular impulse and momentum. Initial angular momentum IA omega 1, final IA omega 2. Because omega 2 is 0, so this means final angular momentum should be 0. IA omega 1 can be expressed in this way using omega 1, kg, and rg. And here we use parallel axis theorem to calculate IA. In the middle, this one, the angular impulse. The angular impulse about point A. Look at this diagram. You can see about point A, AY, AX, W, all these, their moment arms are 0. Only F, this should be considered. And the moment arm of F is RP. The moment of F about point A, this one should be counterclockwise. According to this defined coordinate system, it should be negative. Okay, so here, that's why there is a negative sign before F times RP. Okay, that's our third equation. It seems we can't solve this problem because we don't know F, we don't know omega 1. But if you look at equation 1, you should be able to see the integral of F with respect to time t can be expressed using omega 1 here. if we substitute this item to replace the integral of f with respect to time t in this equation 3, we actually can eliminate f and also omega 1. And finally, we can easily get the relationship between Rp and Rg and Kg. So what does this mean? This means when we design this Chappie test machine, if we can let the relationship between Rp, Kg, and Rg follow this equation, then we can make sure the impact at the pin point A 0 when this pendulum hits the test specimen. The third problem is for explaining how to deal with a problem involving more than one rigid body. So for example here, there is a block. We already know the mass of this block, and this block is connected to a cord, and this cord is wrapped around this disc. Initially, this block has a velocity downward 2 meters per second. It's going down, so it will drive the disc. This disc will be undergoing a rotation about its fixed axis 0.8, and this disc is undergoing a rectilinear translation. The time interval in this problem is 3 seconds, and the task is to determine the velocity of this block after 3 seconds. Okay, again, this is a problem involving force. The force here is the weight force of this block. It's the driving force of this system. Velocity, initial velocity 2 meters per second. The target is its final velocity. And the time here, time is 3 seconds. So this is the problem involving force, velocity, and time. So this can be solved using principle of impulse and momentum. Actually, this problem is also a typical problem that can be solved using kinetic equations of motion plus kinematics. Okay, now the solution. We have defined this problem. We know the disk undergoes rotation about a fixed axis. The block undergoes rectilinear translation. So here we have two rigid bodies. we have two methods. We can consider this disk and the block separately. Another method is we can consider this disk and the block altogether in a system. If we consider the disk and the block separately, then that means we have to deal with the tension force in the code T and T prime. If we consider the disk and the block altogether in a system, then this T and T prime will be a pair of internal forces, so they can be eliminated. Okay, as mentioned before, if we have more than one rigid bodies in a system, when we apply principle of angular impulse and momentum, we have to select one point for every rigid bodies, only one point. So this actually can make the solution more complicated. So in this solution, we will consider the disk and the block separately. Okay, diagram. One is for the disk and one is for the block. We define this coordinate system x, y, and in this one here I define clockwise as the positive rotation direction, because in this one here you can see by observation you can see the direction of angular velocity of this disk will be clockwise. So define clockwise as the positive rotation direction can be more convenient than defining counterclockwise as positive rotation direction. Okay, here we have tension force T, reaction force AX and AY, and weight force WD. All these three forces act at point A. Point A is the fixed axis through point. For this block, there is weight force WB and tension force T prime. T and T prime appear. They have same magnitude but different direction. Okay, here we already know the mass of this disk, the mass of this block. IA is already known, it's 0.4. That's MMI of this disk about this point A. Time interval T1, we can define T1 is 0, so T2 will be 3 seconds. VBY1, the initial velocity of this block, VBY1 is -2 meters per second. We don't know VBY2 and omega D2. VBY2 is the velocity of this block in the final position. Omega D2 is the angular velocity of the disk in the final position. VBY2 and omega D2 based on kinematics, we know they are not independent. Actually, they depend on each other. So this means for these two, actually only one is unknown. Be careful of their directions. Direction of VB2, if it's downward, then omega d, the angular velocity of this disk, must be clockwise. So according to this defined coordinate system, if omega d2 is positive, then VBY2 should be negative. Okay, now we have two rigid bodies. We consider these two rigid bodies separately. So we will apply principle of impulse and momentum on these two rigid bodies separately. So firstly, on this disk, we can list these three equations. The first two along x direction, along y direction, these two for principle of linear impulse and momentum. The third one is about principle of angular impulse and momentum. For the block is undergoing rectilinear translation because we consider this block separately. So we only apply principle of linear impulse and momentum along x direction, along y direction. Okay, now look at equation A and equation B. Because initially VAX, VAY must be 0 because A is the fixed axis through point. So at this point, velocity must be 0. So if we substitute this into equation A and equation B, you will find equation A and equation B are not useful. We don't need them. VBX1 and VBX2 are 0 because the block is undergoing rectilinear translation along vertical direction. So VBX must be 0. So substitute this into equation D, you will find equation D is not useful. So for solving this problem, only equation 3 and equation E will be useful. Okay, in equation E, we have VBY, VBY1, VBY2. VBY1 we already know is 2 meters per second. So omega D1 can be expressed using VBY1 divided by the radius of the disk. Okay, next we substitute all these already known parameters into equation C and equation E. We can get two equations. For equation C, this is about angular impulse and momentum of the disk. For angular impulse, only the tension force from the code can generate a moment. This is t times 0.2. It is clockwise. According to the defined coordinate system, it should be positive. Omega d2 can be replaced by VBY2 divided by the radius of the disk. So this will be our first equation, equation 1. Equation E for the block. This is a linear impulse generated by T prime, the tension force in the code, and the weight force WB. For T prime, because its direction is upward, so the linear impulse generated by T prime is positive. For for WB, it's downward negative, so its linear impulse is negative. Initial linear impulse, because the velocity is downward -2, so this is negative. Final impulse VBY2, also downward, so this is negative. Okay, in these two equations, because t and t prime, they have same magnitude. So finally, only two unknowns. One is t and another one is VBY2. So this can be solved. VBY2 should be 13.0 meter per second. Its direction downward, negative. For this problem, you can try to solve it using kinetic equations of motion plus kinematics. And then you can compare your solution with this solution using principle of impulse and momentum. And you will see using principle of impulse and momentum to solve this kind of problems can be much easier.